team introduce themselves.
I'm Mitch Young. I'm one of the mechanical engineers with the team.
I'm Alec. I'm the computer engineer.
I'm Olsen. I'm another mechanical engineer.
And I'm Hammersley, the electrical engineer.
And as a reminder, our advisors are Professor Alec and Professor Johnson. A bit of background on why we are doing this project to begin with. Currently, mascara is the third most commonly used decorative product. This means millions upon millions of men and women apply mascara almost daily. However, 10 million Americans also suffer from essential tremors, the most common cause of hand tremors in the world. The average age of onset is about 40 years old. This means about when the time that someone may get essential tremors, they've had approximately 20 years of applying makeup experience before they start suffering any of the effects. This can be a damaging blow to mental health, especially if they cannot apply the mascara anymore. The loss of autonomy is devastating. Our requirements for our our agenda before we begin. We'll go through the system design requirements, then our design iteration and inspiration. We'll move into the assembly, both mechanical and electrical. Then we'll go into the testing and results. We'll go through some key takeaways from this year. Finally, we'll summarize, and there will be time for questions. Our design requirements. The first one kind of seems like a gimme. A tremor suppression device should suppress tremors. However, this can be accomplished by simply holding the hand still. As such, we needed to add on the second requirement. It needs to allow for the application of mascara, meaning it needs to allow for intentional movement as well as dampening unintentional movement. It also should be portable. While it's better than nothing to have a device that would be only in your home, ideally a user should be able to use this wherever there is a small amount of counter space and a wall outlet. This is also leading into our next requirement. It needs to be able to be powered by a standard wall outlet, a single plug. Finally, it needs to be safe and comfortable for the user. We can apply all the tension in the world and dampen tremors, but at a certain point it becomes painful, and even I'm not vain enough to use that device. Now we'll go into some design iterations with Mitch.
Thank you, Jackie. So as with every design ever, our project went through a lot of different iterations in its evolution and a lot of different steps. And if it had more time, it would keep going under more iterations because that's how the design process works. When we first started off with this project, when it was given to us in September, our initial reaction was to very much focus on something similar to the lift spoon, which is a commercially available device that it doesn't suppress tremors, but it's a self-stabilizing device that the end effector will always be steady and level, even if the manipulator arm is not. However, because this is already commercially available and it's so small and compact, we thought this was outside of the scope of what we could reasonably do as an undergraduate engineering team. So we moved on to other devices. On the screen are two other commercially available devices that we are looking at as inspiration for this device. The first one, the gyro glove, is exactly what it sounds like. It's a gyroscope on top of a glove, conveniently enough. So this is nice because it does restrict the movement of tremors rather than just solving the issue of shakiness. However, it only solves the issue of restricting tremors when it's out of line of the gyroscope. So if you're moving in the plane of motion with the axis of rotation, it won't restrict the movement of tremors. So we want to look at something that's a little bit more widely applicable. Finally on the screen we have the gimbal, which is an external device used mostly for steadiness of phones and cameras. It's a really interesting device. It's very similar to the lift spoon in application, but because it's a large external arm, we decided to steer away from that. But we still used all three of these for inspiration. Moving on to where we started this semester, we started off with an exoskeleton-like device that sat on the back of the forearm, back in front of the forearm, and was contained to that little location. The forearm had all of the motors, the electronics, everything we would need, and it was a very portable, easy-to-use device in the ideal world. Additionally, it was nice because, as you can see here, the transmission had a very short space where it was being used. So this meant that we only had like 6 inches of space where we needed to connect the motors to the hand. This meant there was less space for failures and kinks to happen along the way. However, when we were looking for motors to restrict the movement of tremors, we ended up getting bulkier, heavier motors than we had anticipated because those were the ones that restricted the motion of tremors completely. We ended up with 2 very hefty NEMA 17 motors, which we regret having such large motors. So in the end, it became too heavy to have this on the back of the device because the user would essentially be weightlifting every time they use the device, which, sounds great for great muscle gains, but it's less useful for the user and less comfortable. So we decided to move on to a different device. We sacrificed the portability of the last design in order to make it a little bit more comfortable for the user and take the weight off of the arm. Additionally, this also gave us more room to work with the electronics and more design freedom because it wasn't constricted to the size constraint on the back of the hand. We now went to a device that sits on the tabletop, and we have a transmission connecting from the tabletop to the wrist, which restricts movement of tremors. However, while this takes the weight off the arm, it also sacrifices a little bit of portability because now you have a tabletop box that requires a surface to be placed on. It also requires a longer transmission. Rather than having that 6 inches of transmission we had before, we now need to extend our electrical cables and our mechanical transmission from the tabletop to the hand, which requires more connections, more kinks that can fail, more things we need to be worried about. And in the end, we were hoping for as simple of a device as possible because then it's more likely to be fail-safe. However, we only had a small transmission with this, and it was still workable. Moving on, Alec will talk about the assembly of the overall design.
Thanks, Mitch. So, like you said, now that you know what it is that we were trying to accomplish and the general idea, Bailey and I will be covering the different parts of the assembly. I'll be covering electrical and computer because I'm biased, and then Bailey will handle the mechanical. So for our logic flow, we decided to go with a 2-phase system. The first phase was a calibration system. The yellow LED will turn on when the user presses the button. At this point, a reset timer begins. This timer can be adjusted. However, for our purposes, we decided to go with 3 seconds as that seemed like a safe starting point. If at any point during this calibration time, the IMU detects motion in the z-axis, which goes with the user's hand, of 0.5 meters per second squared or higher, it sends a signal to tell the motors to tighten. Once they tighten, the timer then resets back to 0. If it manages to make it through the entire calibration timer without having done another cycle of the motors, this meant that we had isolated the tremors down to less than 0.5 meters per second squared. And we could move on safely to the second phase, which was the compensation phase. The compensation phase essentially was a loop of using that same threshold acceleration, but this time using it for a separate purpose. Anytime it detects 0.5 meters per second squared in a specific one of the 2 directions that it was searching for, one motor would tighten and the other one would loosen. This allowed us to keep that tension on the hand and keep those tremors reduced without sacrificing mobility, so that if they were to move this way, one would tighten while the other one loosen, and vice versa. Moving on to the electronics of this, we decided to go with a breadboard PCB. This allowed us to keep the simplicity of the breadboard's copper lining while not sacrificing the ability to solder the pins into place and keep them from coming out if the device shook or anything. So the center of it is the Arduino Mega. This has obviously power and ground, and also has a bus line going from the IMU to the Arduino. This allowed us to get the data that told us if we were crossing over that threshold. We also have a bus line going from the Mega to the PCB. There are 8 wires that go through that, 4 per motor driver. We have 2 motor drivers. These send the signals to tell the motors to run. Motor drivers sent it to the motors in the correct order to get them to do what we wish. There were also 2 more wires in that bus. Those are the ones coming from that power line into the PCB. This allowed us to power our Arduino in the first place. Finally, we have 2 more wires going to the LEDs and 1 going to the buttons to give us our user interface. A yellow one for calibration, green for compensation, and an on and off switch. I'll now pass it over to Bailey to handle the mechanical portion.
So moving on to the mechanical aspect of the assembly, the transmission is the part of the device that does the actual dampening for the system. It consists of a set of pulleys, bike cables, and elastic bands. The control of the transmission comes from the motors, as when they rotate, they turn the pulleys, and when the pulleys turn, it pulls the Bowden cable, which is in the bike cable, and then the Bowden cable will stretch the elastic bands. When the elastic band is stretched, it provides a force on the hand, which then dampens the tremor and then makes it easier for the user to apply their mascara. One of the more crucial parts of the of the transmission is the clasp. It acts as an anchor point on the arm for the sleeve of the bike cable to attach to. The Bowden cable is threaded through the hole on the clasp and is connected to the elastic band on the back of the hand. This provides a more linear tensile force, making it so that when the wrist moves, it feels like more of a natural movement. The clasp was designed with an ovular shape so that it fits more comfortably and securely around the user's wrist. The team also added a slot near the joint of the cuff so that we can add a band with a buckle or a strap with a buckle wrapped around the cuff, which makes it easier to adjust the tightness for people with larger or smaller wrists. The housing is part of the mechanical assembly that contains the motors and most of the electrical components. The box itself is designed to sit on a flat surface near the user, giving them enough space to be able to freely move their arm while they're doing their mascara. The team was originally manufacturing a housing made out of wood. However, as we were adding more components and pieces to the box, it ended up getting too close to our 10-pound limit. And so then with that, the team decided to change the design to a prefabricated aluminum box, which cut down on nearly half of the weight, making it easier to carry the device around. Moving on to the testing portion of our presentation. The requirements that the team did meet, so for the motion dampening test that we did, one of our motors was down during the time of testing. However, despite the motor being down, we still had one going, and so it was able to dampen the tremors within our required range of 4 meters a second squared to 0.5 meters a second squared. With the one motor being down, we just weren't able to enter into the compensation mode, which allowed for intentional movement. However, even though the device stayed in the first phase, it was still able to meet our motion dampening requirement. The hyperextension test, the maximum angle that the device pulled the wrist to was 20 degrees, and the requirement was 40 degrees, so that was within our limit. The weight of the device ended up being a total of 5.6 pounds, which was within our requirement of a 10-pound limit. The containment system, the cuff, and the glove all passed the ingress protection test, giving it an IP rating of 21, which means that no small pieces can get inside, and it's not affected by dripping water. The accelerometer wasn't included in this test because it's placed on top of the hand and it's only covered by a piece of fabric. We didn't want to drip any water on it so that it would risk any potential shocks to the person who was using the glove at the time. And then finally, the device was able to be powered by a standard wall outlet. So some of the requirements that we didn't meet were portability as well as temperature and sound. Our requirement was that the device had to be able to fit within the confines of a 12-inch by 5-inch by 5-inch space. However, our box ended up being 8 inches by 6 inches by 3.5 inches, which was 1 inch outside of the requirement. And then also, we did not want to perform a drop test with the device because the electrical components within the box ended up being very fragile, and we wanted to withhold the drop test so that we can maintain the functionality and be able to do tests and for future use and everything. So the device also maintained a steady surface temperature of 74 degrees Fahrenheit, which was within our requirement range. However, it was measured at 80 decibels for the sound intensity, and our requirement was 60 decibels, so that one, it failed that requirement. So then, moving on to the key takeaways, I'll hand it off to you now.
Thank you. So for our key takeaways, you could hear from several different group members that we had a lot of issues with our motor size. With that being said, if we were to go back and look through this project and or do it again, we would definitely try to select a better motor and look more into detail about what kind of motors this project would require. Along with that, our motor drivers, we would go back and try to find motor drivers that suited that motor's current pull as we go through and look through that again. Secondly, our communication. Towards the beginning, since we were all new, we didn't know one another since mechanicals and electricals are being brought together. We would actually try to work on our communication. Of course, now I can say that we've all probably become friends. But in the beginning, it was a little rough because we were shy and nobody really wanted to converse with one another, because that's how it goes. Thirdly, we would like to prepare better for meetings. I guess you could say now that everything when we go through the semester is already written for us and we go through and do the schedule. But however, in the beginning, I feel like it would have worked out better since we went through 7 different iterations of this project, possibly if we had more of a structured layout rather than be on time, sit down and get the work done. And lastly, the biggest thing we have learned is that theory is not the same as practice, because if it was, the first project layout we had probably would have worked. But it didn't, which led us to our last and final choice of this project. So for future improvements, going back about the smaller motor, the motors that we did choose currently, I remember stating that they actually cost about $32. Now NEMA 17s can be small, however the choice of the motor that we have had an attachment towards the end when you could see in a previous slide, which was like a black box, and we needed that because of the sole fact that it stopped any, I don't think of the word, anything that it would stop. Back drive, thank you. So, which would hold Jackie's arm steady when she was trying to go, and it wouldn't pull any more on the wires. So, that being said, if we had more time and money to budget into this in the future, we would probably choose a more expensive motor that could be a compact size. So secondly, we would probably clean up the wiring. A lot of the soldering that we actually get to hide inside of the device box is a little messy. With that being said, we would probably buy better wires to solder with, because since we're connecting a lot of these to the Arduino Uno, some of them we couldn't drop test because they would either become unplugged or just actually rip off of the solder that was put into the PCB board. Thirdly, we would like to waterproof the IMU. I'd like to state that it would probably be well to do that, since obviously if any customer were to be using this in a bathroom while applying mascara, they would probably be near a sink where water would be and they could hurt themselves. Fourthly, we would like to encase the wires for the IMU. As you can see in the photo, it's very faint, but there are some wires that are just shown there. The idea of putting the wires like that began because we were trying to make it easier for the customer to just unattach and reattach the IMU, since it would be stuck on top of their hand. However, the reason that they're uncovered for the time being was just so we could use that too as well. In the future, we would like to cover that though, just so anyone wouldn't hit the wires and or hurt themselves. Along with that, I'm left-handed. So with that being said, we would like to do a future change or just improvement of making this device not only for right-handed people and making it for left-handed people as well. And lastly, for our specific focus within this project, we focused on the C direction, since mascara mostly is like an up and down motion. However, in the future, if anyone were to conquer this project, we would suggest to do lateral and medial motion. Alright. So in summary, we went over our design requirements, we went through the evolution of our design and our final design choice, we went through the electrical and mechanical assembly of this project, and I went over the key takeaways. Thank you. Are there any questions?
Professor Will?
Can you go back to slide 11? Removing for operation.
That's me.
Okay, so you've got like a little picture of a complex receptacle, like a wall receptacle there, and then 2 lines, and it's going to the PCB. So you plug in your PC, you got like cord going directly from the wall to your PCB.
So, first of all, this question is, do we have power going directly from the cord, or from the wall to the PCB? No, we do not. We purchased a device that brings it down to a voltage that is not going to completely melt the board. I can't remember the actual name of the device at this point, but when you plug in on the back, there were options for whether you wanted that to come out as 6 volts, 9 volts, 12 volts. So we brought it down to 6 volts, which is what we needed. It then goes into, the power and ground goes into one of these 2 rows, and then from there gets sent back out to everywhere that we need it.
And then I think those are LEDs, and then below it there's a little square with a circle. Is that?
That would be the button. It's just a
Professor Will was asking what this was, so button.
So then it's just one wire going to the button then?
So, I guess it'd be Professor Will was asking about the specific choices in the design of the button. This is just this is a very, very simplified version of the actual circuit diagram. The actual one looks more akin to a rat's nest than this.
I can show it to you.
There is there's a resistor, there's the typical stuff to make sure that it will be pulled down when we don't want it to be active, and then can be activated at any point.
You got 4 wires going into the motors, the separate motors, right?
Yes.
So you got separate drivers somewhere?
Easier if we go to the actual
Yeah, let's
circuit
just
diagram.
pull up let's go to that.
This is a simplified schematic for the presentation.
All right.
We have the actual wiring diagram afterwards.
So here's our full circuit diagram. Like it's a lot less pretty. So yeah, we have H bridges on the PCB board. That's what's mainly going on in there. So it gets power both from the Arduino and from the power supply into specific ports on it to handle both the logic output and the actual power to run the motors. So I don't know if that helps clear up things. We didn't want to weigh down the presentation with too many wires.
So was there any virtual design validation done before you purchased the motors? And also, why did you choose stepper motors versus other types of motors?
So Professor Blood's question was there any virtual design done before we purchased the motors, and why did we choose stepper motors? We chose stepper motors for the simplicity of the coding, so that way if it hits this much you can do step 1, and then the gearbox that we have, warm gearbox that we have on it will stop the back drive, so that will allow for the mascara to be applied, and so if it pulls this way it'll stay here. The virtual design, we did do an ASA for the different types of motors. We came to the conclusion that the stepper motor was probably the most cost efficient for what we wanted it to do. We did look also at brushless, but we determined that that was out of the scope of our abilities at this time.
So going forward, if you were talking about trying to purchase more expensive motors, it just makes the whole system more expensive, correct? So in hindsight, how could you have realized that the stepper motor was probably a poor choice for your design?
So Professor Blood is asking how in hindsight could we have known that these stepper motors were a poor choice? We could have done further research into just the NEMA 17 motor itself weight. The gearbox was a little bit of a strange type. It did come from a source that you can get multiple copies of it, but it is an international site that didn't give too many details aside from the torque ratio. So we did the virtual design based off the torque ratio from the gearbox. But in hindsight, we should have known that that torque did wind up being